Our next speaker is our first keynote speaker today. It's Professor Whitney Newey. Professor Whitney Newey is a distinguished member of the Department of Economics at MIT, one of the most esteemed economists and econometricians that requires no introduction. So holding a PhD from MIT Economics, he has taught at Princeton, chaired the MIT Econ Department, and currently the fourth professor of economics at MIT. Professor Newey's exceptional achievements are numerous, from being the Everett Sloan Fellow and a Fellow of Econometric Society to more recent recognition as a member of the American Academy of Arts and Sciences and a distinguished Fellow of the American Economic Association. His research contribution arose as associate editor and co-editor of the Econometric Journal, along with his dedicated service and on the executive committee and as its council member has profoundly shaped the direction and the quality of research in this field of research. So Professor Whitney's talk is going to be automatic debiased machine learning model.
Thank you for the thank you for the invitation to be here. It's wonderful to be here and learn from you, and also get to share some things about device machine learning today. I appreciate the invitation. It's been some time to the City University before, and a wonderful place. Work down here and wonderful hospitality. Great to be here. Okay, so this is talk that is going to cover and include some things from three different papers. The first paper is a joint paper with Victor Zurkov, a student at another Victor, Francis Martinez, and then Priscilla Fergon. I'm going to focus mainly on that talk. Actually, I'll get background things so that they can talk about device machine learning in general and what the issues are and how to do it. So, and then the main contribution of this talk is from that paper. Okay, the main contribution to this talk. And then two other things that I'll also speak about are the other papers. The second one has Monte Carlo, and it's really useful and shows how well the things that I'm going to talk about today can do in particular Monte Carlo design. And then the third paper has an application. Okay, to doing the data. All right, so let me introduce ignore this paragraph. For now, I'll come back to this. There are really interesting arguments that depend on the design. I can think of conditional expectation for the purposes of most of this talk. I'll just think about a conditional expectation and then one of the paragraph. We'll come back to that. But the talk covers things much more general than conditional expectation. Generalized linear models, which you may have heard of, okay, but for most purposes in the talk, we can talk about that. There are lots of interesting things that depend on the reaction. Average treatment effect is become super interesting and popular over the last 2 years. Average derivative that is a nice measure of the average effect of some variable. It's actually, you can think about it as average treatment effect for continuous data. And then also there are applications directly in economics, having to do with estimation of structural models, dynamic discrete place models in particular, where there are unknown things, traditional trace probabilities, and the general condition is very probability, and you can use regression to estimate those, the formula of the structural changes in terms of the regression to estimate. So many interesting objects depend on the regression. And recent developments in machine learning have enabled us to estimate regressions which we couldn't estimate before. High dimensional and particular high dimensional regression. And the motivation for that is clear for the average treatment effect. For the average treatment effect, we need just the right set of regression to have the conditional independence assumption be satisfied. So if that right set of regressors happens to be a lot. Okay, this machine learning provided the potential to allow for a lot of regression in the average treatment effect. Okay, and then the conditional price probability might have any stage that help determine the first probability. And so we want to allow for many of those and estimating the regression. So it leads to pretty naturally and very interesting machine learning at this point. But we don't have to talk a lot about this, I don't think, at this point, but it's a natural thing to think about using machine learning to estimate high-dimensional regression. We're focused here in this work on estimating a parameter associated with that regression. Okay. Average treatment effect is one example. Structural parameters that come from probabilities or other kinds of parameters. Our focus is going to be on estimating parameters. So we know, right, the neural nets amazing performance in doing predictions in certain settings, lasso as well, and also in doing prediction, brand force as well, in doing prediction. Okay, it's machine learning is good for prediction, but it's inherently biased by regularization and or model selection. What are we talking about regularization? Well, lasso, right? The two things stand for strict reasoning. The essence stand for strict reasoning bias. Right, so the strict biases, your estimates, your lack of estimates, and the selection does as well. It's a little more subtle, but it's still there. Regularization is also present in most applications in neural nets. It comes in the form of LC penalization, rich type penalization. It comes in other forms too, where what you do is you take your own app, you get some starting value, you iterate for a while, and then stop. And then try some new starting value, you iterate for a while and stop. And then you combine those, different estimates, that's the form of regularization. We don't know a lot about its theoretical properties, but it certainly has some bias associated with them. And then random forest also has regularization model selection bias. So problem is for many parameters, those biases transference to the formula for the parameter in terms of the regression, the bias is passed right through to the final estimate of the parameter. And that's the problem, actually, for Pascal, for example, in particular, the bias is large. And a good example of that bias is large and is going to mess up inference. You get that confidence interval. If you ignore the bias, that confidence interval is in standard procedure that are not going to work. That have a large bias into them, and the result has terrible coverage probability. Okay. A solution to this regularization and model selection bias from many parameters of interest is name and orthogonality. What that refers to is setting up your estimating equation so that the fact that the machine learner has zero, the first order. So the first order, there's no effect of the machine learner on the estimating equation. Okay, and that's the orthogonality, and also uses property. And there's some references to early independence control and recent paper, starting papers by Maloney and Drop and Henson, early on, and then also, some of these work on this stuff. Okay, so that's the solution that we're working with. There are other things you can think about during different times, but anyway, that's the solution we're working with. Develop name of the hormones, moment functions, and the other one, the orthogonal functions where the stimulator has zero first order effect. Okay, and that eliminates then, the first order eliminates the bias that is caused by the machine learning. Okay, so we'll talk about that in more of this. Let me give an example first of how bad this bias can be and how the orthogonal function is prosecuted and how to correct it. Okay, so here's an example. If the linear regression model is a lot of the test, right? This is something to this last one that you apply. You have a yi is equal to beta naught times b plus not b plus the covariance, a lot of covariance, many potentially more than the sample size. So this is the standard line code type setup, okay? Where you could think about estimating this by last one. The plugin estimator thing on is very biased. You just do last over here and you need to coefficient on that is terrible for confidence intervals. Okay, it doesn't work. Okay, we I'll give a Monte Carlo example just a minute. It's a little different kind of plugin estimator, but same thing applies. You get terrible coverage if you're going to bias. Okay. So the plugin estimator is there now that coefficient on the variable interest is very biased. Okay. For last one. And then you can hear how you create the way you create the orthogonal function is one thing to do is the covariance. Okay, so this is Bologna, Curtis and Johnson, Review Economic Studies paper 2014. And what you would do to do is what you might call double lasso. Double lasso, you do lasso regression of y on the z's and d on the z's, and from that you get predicted values from the lasso regression. Okay. And then you regress the residuals from the lasso regression of y on z on the residuals from the regression of d on z to get that happen. Okay, so that's pretty good. They use that, linear model, where we have, say lots of different factors on things, they will do that, and you take residuals for y and residuals for the variable vectors, and then regress the y residual on the residual. That has to be that. That has to be effective be biased. It creates an integral cardinal function. Okay, and so it's the first order is biased. Okay. Now there's also about the same time that paper was written, there's also several papers on debiased Glasgow. And that does it another way. It actually is this. It's a version of this, but it does it another way. And I'm going to not get into that. I think there's a whole discussion of another literature. And so the debiased Glasgow also does this, thankfully. Okay, but this is a simple way familiar from econometrics and independently developed, even like co-author would say, prior developed. And published in finally in 2014 in that review of economic studies paper. Okay. Okay, so as part of something out is like Robinson. That's the early he wrote about semi-parametric estimation of a model like this, where this is some unknown function, and there's he parsed out the covariance, the residuals from a non-parametric regression of y on z and b on z, and regress the y residuals on the b residuals and analyze that. So that's a very nice early paper on this. in terms of searching for an orthogonal loan function, or estimating the first data file deal first order of the fact. You know, it turns out that, you know, this part on that Einstein. And so this produces an orthogonal loan function. And then let's just look at some graphs and compare the distribution of the plug estimator with the device machine learner. And this is based on random forest. Okay, so what you're going to do here is the random forest regression. You take the predicted values for Y associated with disease and do the same thing for the predicted values of D from disease. Okay, and I'll take the Y residual for random forest, and the rest of the D residual from random forest. Okay, the graph on the left, that's the non-debiased thing. So that's the bias thing, and this is random forest with the last electric is bad, but a little different. Okay, and so you can see there's a tremendous shift. So this is the nominal distribution. That's the thing you equate the distribution your T ratio is, right? That's the nominal distribution. That's what you're using the critical values from to get your confidence interval. And what this is the distribution of the T ratio when you know, just ignore the fact that you got machine learning in the first step, and you take the T statistic on that data. And if you can see it's terrible, it would have terrible coverage, very far from 95%. And so, you know, the inference is very bad here. If you just plug in, random forest estimator and estimate this, it's net zero coverage. The one on the right, that's what Hartman now gives you. And so it doesn't get rid of entirely the bias, but gets rid of enough to get good coverage probabilities. Right? It's sort of the great majority of them. Okay, and so this graph is repeated over and over again. You can try it last one, you get the same thing. You can try it neural network regularization, you have the same thing. It's repeated over and over again, and it illustrates the problem. You know, if you just do that though, or some other machine learner, you plug in that and into whatever your formula is, you get a bias that is true. In last those days, they have theory, actually, which says that what happens actually is a sample size gets big over here, is this thing very incredibly far away from that red line. Okay, there's a constant term in the bias class, so it goes up and going to be a great B down. So it's you know, bad. The bias is bad. Okay. All right, so that's an example. It illustrates that. Okay, so let me go back and I'll talk about naming orthogonality for a minute. Okay, what that means is there's no first order effect of the machine learning on the moment. If you're think of genome estimating some parameter, then there's you have a regression that there's parameter that just depends on, and you use some volume functions to try and identify the parameter of interest. Okay. The way that we do your normalization, what we do is we take an identifying moment and we add to a bias correction. That bias correction is what's called the non-parametric influence of the expectation of the identifying moment. Okay, the value is just the generalized regression, the value of the regression. So what this is saying is there's for every identifying moment and every first stage, there's a correction. Okay, for every identifying moment, pick one, pick any one. And for every first stage, you're looking important and there's a correction. Okay, and so that's what's in this paper. This is a way to generate a moment condition that has a model-free orthogonality property. It's not dependent on the spin. It's a bias correction that's constructed specifically for whatever your first stage is. Okay. So it's different than substituting regressions, such as Glasgow for conditional expectations and efficient scores. And sometimes you hear that the rate bias is used in efficient score, is you have to qualify that a little. And what we do is a bias correction that is specific to the moment condition and is specific to the first phase disease. Okay, and it differs from using an efficient score. You can think of that as the efficient score. For the bias corrected moment condition is an efficient score or efficient influence function for a particular problem for non-parametric estimation. The parameter you're interested in, and it depends on whatever the first stage. Okay, but it's different than the approach that was taken previously. So different. Substituting regressions like lasso for conditional expectations and efficient score is not robust in this way. Okay, and that's a paper Tom pointed this out in the analysis. Analysis the different paper. So the method that we have in this paper, we'll use today, is distribution free, non-parametric. It produces an orthogonal moment condition. The orthogonal properties don't depend on anything other than some regularity conditions. Okay, so so for example, the standard errors you get are robust in this application. As long as it's exactly identified the moments and hours identified, they're robust in this application. Okay. They don't have to worry about it, like an adjustment like Tom talked about. The automatic in the title prefers to be biased and based only on the object of interest. Okay, so we like to construct something where you don't have to know how to be biased exactly. That you could just use the first step you got and use what the thing is you're estimating, and then you can construct to be biased. And that's what we do in this first paper that I'm going to focus on mostly today. Okay, so it's automatic and only depending on the object of interest. You don't need to know the exact formula for the bias correction. Actually, you just need to know the thing you're estimating, and then you can construct the bias correction. So what this is designed to do is give an end-to-end algorithm where you have a moment conditions that identify some parameter interest that depends on the reflection or some other reason function that you estimate. You want to estimate it by machine learning to depends on high dimensional. And just given that, you can go and use just those two pieces of information and start a bias. Okay, so kind of what we're going for is an end-to-end algorithm. Where you have an estimator that you can use to estimate the unknown function, your moment condition. You have a moment condition, and the algorithm produces a bias correction for just knowing those two things. And so that's what we have. And we'll talk about today. Okay. So it looks earlier was automatic biasing in this paper with Victor to the top and the whole thing. That was good for lasso. And what I'm going to talk about today was exploring first step. Neural nets as a reinforced version actually. Okay, so it extends what we did for lasso and earlier was any first step, including neural nets and exam for it. Okay. So now, what the automatic part of this is the following. And during this biasing, there's thousands of something you don't know and have to estimate. So there's an alpha function that generally depends on it depends on an unknown. I mean, you're talking about the function, but depending on this alpha, it's huge. It's important to be biased. You have the right alpha to be biased. Okay. And so here we give an automatic estimated alpha. So based only on the object of interest when we're done. Okay, so well, it's saying end-to-end algorithm, right? I can get once You have to identify the moment condition, and you have to put your action in that form of it, and then, you know, we give you a method that you can then just go and apply to be biased. But, the primary innovation of the first paper is standardizing alpha naught is the minimum of an objective function. It depends only on the upper dimensions, with neural nets nodes that can be applied. Okay. And the paper also innovates in giving statistical guarantees for that. You know, in other words, converting traits or actually even finding sample inequalities for that. I'm going to not talk about those very much today, but they're in the paper. And I have a slide if you're interested. Okay, the paper also innovates in giving estimators and giving other generalized rate of reduction. Okay, so if I go back to that first paragraph, you know, this is what we do. Sorry, that's what we do. You know, we do this for, in other words, we give a bias correction for any generalized linear regression. And what is that? And the idea is, you know, whatever the first step is doing, it's estimating the element of a closed linear set of functions and sets the possibly non-individual or bottom of all elements of that set of functions. So this includes generalized linear models, you know, from statistics, they include lots of other things, quantile and so on. So there's many additional quantile. What they do in this paper, I do a lot of stuff to put some arguments like them and for lots of other things. Okay, so that's just to make it as general as we know how. Okay. Well, let me, you know, I'm going to stick down, like I said, with the benchmark retention of being the first step. You know, think of an unturning progression of some kind, neural nets in particular, focusing on, I'm going to stick with that mostly, but it can, you know, we want to make clear that what's in the paper applies to any sort of retention. Okay. All right. So now, one of the other features that we're going to use is cross-fitting. So this is also built into the algorithm, looking at cross-fitting, where we estimate the neural net or the machine learner from one data set and average over another part of the data set. Part of the data set is estimated the machine learner, or create the machine learner, and you average over the other part, and then you identify moments. And also been around for a long time, but one they do routes. So this is based on that, we said partly the after, so okay. We use it here, and what we get is root inconsistency in aspect of theory, root inconsistency in aspect of cardinality for an estimated object of interest when the regression and outcome of estimators is each sort of consistent, and the product of the divergent space is faster than n over 1/2 and the minus 1/2. Okay. The second paper gives a Monte Carlo comparison of the state of the art, dragging that for estimating the average treatment effect of the neural net propensity score estimator. So what we're going to do there is we're going to compare how this automatic method works versus what has been the approach to the average treatment effect in the rest of the literature, and almost all of the rest of the literature, which is you have a totally robust moment condition, efficient score, or whatever you want to call it, or efficient influence function, inverse of the propensity score, and the rest of the literature on machine learning and what it's done. It has estimated propensity score by some machine learning method and plug it into this format and use that. This automatic method doesn't do that, it does something different, and it works a lot better than the state-of-the-art method where you use the inverse propensity score. Okay, I'll be the bottom line from that. And right, we found there, and I'll show this, that the automatic device machine learner was significantly more precise than the other robust estimation based on the inverse propensity score. Okay, so that one we should say that one's already published in the conference volume for 2022 at the National Conference on Machine Learning. The third page of your application, and then I have time to get to it. Anyway, it's nice application and public finance. Okay. And this word, I just want to highlight the difference. We're not depending on a particular formula for alpha not, or it's biased function. We're going to do an automatic measure of the rating. It does go on this previous one, the last of the automatic bias. Okay, so on the equations, okay, so this denotation of the paper, W is a vector of is one observation on a data vector. Okay, it could be very large dimensional, of course. It includes an outcome variable Y and the rest is X. We here consider parameters, again, keep things simple as we can. Just look at the conditional mean. Okay, so the gamma naught, the unknown function has the conditional mean of Y to the X. Okay, the parameters we're going to look at depend really on this conditional mean. So it's a very good conditional mean plug in. There's your identifying moment condition, which consists here's just a formula for data naught in terms of a function that depends on the data and the regression. Okay, and this gives one kind of identifying moment condition. What we're going to talk about applies to everything that looks like this, or every much more general moment conditions than this. But for the purpose of this talk, I'm just going to focus on the kind of moment condition. This kind of identifying object, identifying moment condition. So the parameter is expectation of a function of the data, and it's also a function of the regression. So the gamma W gamma is the scalar function of a possible data observation W and a possible regression function gamma, and we're going to focus on the case of this is linear. Now in the paper, that allows this to be nonlinear gamma, and gamma not to be a conditional, but something besides the conditional mean to be this generalized linear regression. Okay, and this is what we mean by that, for those who are interested. See the paper. Okay, so in this talk and all of this work, you do need, in order to do this debiased, you do need something. Okay, and we're going to focus here on the case where the expectation of this function M has a particular representation. It turns out that there are many interesting examples, including average derivatives, the average treatment effect, where when you take the expectation of M as a function of gamma, it can be represented as the expectation of some alpha naught times gamma of X. So think of this as a function of gamma. Many interesting settings you can represent the expectation of M W gamma as expectation of alpha naught, some alpha naught times gamma of X. Okay, and this holds for all gamma that defining second moment. Okay. So that equation, existence of alpha naught, okay, that has that property is equivalent to this being mean squared continuous in gamma, which in turn is a necessary condition for root consistent mobility of this object. Okay, the object again is parameter, right? The parameter is this. In order to there to exist any root consistent estimator, you have to have this. Okay, and that was shown in some earlier pages. Okay, so you gotta have this anyway to get rid of consistency for anything. And so it's very general in that sense. Okay, there's this good alpha naught. The fact that this is alpha naught is not an accident. This is going to be the debiased function. Okay, that we're going to have to estimate to do the debiased. Okay, and we're going to refer to it as the debiased function because of that's important role. Okay, so what is it for the average treatment effect? Those of you familiar with treatment effects literature may find this familiar. So the average treatment effect here, X, the patient condition arm consists of the treatment indicator, 0 or 1, and the covariates. The regression is, depends on the treatment indicator D and the covariate C. Okay, so these treatment indicators are the covariates and the parameter interface, the average treatment effect can be expressed in this way. The expectation of the reduction evaluated for the treated minus regression for the untreated. Okay, the expectation of taking over the covariate values. This data not is the average treatment effect of potential outcomes of even dependent on treatment, conditional on covariates and the propensities for never equal to 0. And it's from Rosenbaum and Rubin. In this case, the alpha naught that has this form. In other words, for this functional here, and that's the M in this case, it's the regression evaluated at 1, and Z minus the regression evaluated at 0. For that M, this is the alpha naught. Okay, that gives you this equality. Okay, this is well known. This form of the unknown function that shows up in bias is actually well known from earlier work. For the average derivative, okay, so what would that look like? It's based on Stoker's idea of an average derivative. It's also the average treatment effect of continuous treatment. Here, actually, B and Z. Where D is now treatment, and it's a continuously distributed treatment, and Z are covariates. The average derivative is the expectation of the derivative of the regression with respect to B, taking the expectation over both B and Z. Okay, and here the M is of course just the data shows up through action here, and the gamma shows up in M is just the derivative. Okay, so here's the M, the alpha naught, and there's this. There's the locations for the additional density of the negative. In the taxable income application, we actually consider a different slope. It looks like this instead. It turns out to be easier to work with numerically, and so we just do the difference closing. That's not the same as this, but it's it gives another way of thinking about an average effect of some continuous variable on some outcome y. Okay, so the main orthogonal moment function, which is this is from this earlier paper for this, is if you take M minus theta, that's the identifiable condition. And then the thing that you add to it, the bias, is alpha of x times the non-current residual. Okay, so that's the main orthogonal moment condition for this. Okay, for all of these, they all look like this. Okay, so the demonstration of this is main orthogonal is simple. If you look at the expectation of this function, evaluated the true parameter, and evaluated the hidden gamma and the alpha. Looks like the expectation down there, the evaluated the true parameter there, and this is the expectation of alpha times y minus gamma there. Right, well now just do a couple of things. This is right. You already know that this is the expectation of alpha times gamma. Okay, so that's where that comes from. This comes down from here. The theta naught, that's the expectation of gamma naught. So that's the expectation of alpha naught times gamma naught. So that's where that comes from. And this is the iterated expectation. Here's the alpha. And then take the expectation y given x. Here, your expectation can just get gamma naught. And then the second part is minus alpha and gamma. Make this collect terms, right? And then you get the expectation of this thing is the true parameter and any gamma and any alpha is minus the expectation of alpha minus alpha naught times gamma minus gamma naught. There's a Debiased. Okay, it's second order in the difference of alpha and alpha naught and gamma minus gamma naught. Okay, it's also that gives it the name of orthogonality property. It's also doubly robust. And this is for all of these classes things. This is from the paper, early version of 2016. Okay, so that's the name of our talking enrollment condition. So that's what we'll use to estimate data. That's what you guys can learn with data. Yeah, the rate wall is the thing you have to do in order to do that. You have to estimate out the cost. Okay, so that's the next thing you want to take care of. So let's talk about how to estimate out the cost. You need an estimator of this device for applications. So turns out it can be characterized as extreme of a particular objective function that you can estimate. Okay, so how do you do that? Well, just look at alpha naught, and of course, you know, alpha naught minimizes this, right? You know, the only way, you know, you get zero when alpha is equal to alpha naught, otherwise you don't. Right, so of course it minimizes this, and now just square that out. Right, so alpha naught is the minimizer of the expected square difference of alpha naught and alpha. That's minimized over alpha, you know, clearly. So just square it out. You get R over alpha, the expectation alpha naught is the minimizer of the expectation of alpha naught squared minus 2 alpha naught alpha plus alpha squared. Well, this leading part doesn't depend on alpha, so you just drop it out and do your minimization. Okay, so it's the minimizer of the expectation of the second part, plus the expectation of this third part here. Okay, so minimizing alpha not minimizes this objective function. Okay, well here, right, you have the expected product of alpha naught of x times alpha. But, you know, by the representation that we have for the expectation of M of alpha, this is just the expectation of M. Expectation of alpha of M. Okay, so we just replace this. If we've got the unknown alpha naught by something that we know, okay, which is M of W alpha. Okay, we can do that by that representation. And so you get alpha naught, you plot the two terms, alpha naught minimizes the expectation minus 2m W alpha plus alpha squared. Okay, so alpha naught minimizes the objective function, depends only on m and alpha. Right? So it only depends on the object you're interested in, only depends on alpha. And so you can just use that to estimate alpha naught. Okay, that makes that's the automatic part of the device. Okay, so how would you do that? Well, take the subjective function, right? You got, you know, plastic, you know, ammonia, others, you know, extreme estimator, right? So I want to estimate this alpha naught. I have a population objective function that I have not minimize it. I just replace the expectation with example average, and you know, I have to do something about the fact that the functions, I minimize whether it's some class and functions that you can do in a finite sample, and that produces that produces an estimator of alpha naught. Okay, so here's the general form for that. Alpha naught minimizes the sample average of the effective function with the expectation replaced by the average and some penalty possibly. Okay, and you minimize it with some set of functions. Okay. Okay, so that's our automatic estimator of alpha. Yes. Automatic estimator of alpha doesn't use anything other than the parameter right there. Okay. And you can do this alpha. Okay, alpha. Okay, so that's a long way to go for this, but that's the innovation in this paper is we now have an end-to-end algorithm for all you need is the object you're interested in, that's the M, and you need to parse the gamma path. You're going to use that to construct this, and then from the M and also from the nature of gamma hat is that with estimating price, which you can use, you can minimize over some set of functions, and you can minimize this objective function. Okay. There it is again, repeat. The estimator is automatic and only requiring him. You can not use any explicit formula for alpha dot, and here's what it is for the ADE. Okay, you would just put in whatever your alpha is, whatever class of functions you're memorizing over, for here, you just put in the M. Okay, put alpha into that M, you multiply by -2, and then inside the alpha squared, here you memorize this, that gives you automatic estimate for the average treatment factor. Turns out, for those of you who know that literature, this is the first order condition to the sort of balance getting place. Okay. We mentioned that actually in the earlier paper. Now, one of the things about this is that it's very general class of things here that you can allow alpha to be, and some neural nets have been included. Okay, so you can a set of neural nets, and then you minimize this objective function over a neural net. Okay, and there's a neural net estimator. Okay, this alpha. It's estimated off the primary innovation in the first paper, and then we have convergence rates for neural net and the generalization to M W gamma, nonlinear and gamma, and generalized linear regression. And it generalizes the earlier paper and allowing something besides lasso. So the earlier paper is a lasso type of objective function, and it does look like that. But this paper, we didn't know at the time that you could do the neural net by just changing the function set of functions. So that's what we do in this paper. Okay, and we also use cross-fitting. So here's now the end-to-end algorithm. Okay, so use cross-fitting to do this. Particularly on the basic set and the L distinct subsets that are equal size. In practice, L5 often or L equals 10 is often used. Similar to cross-validating and fitting a regression function to do with the literature on this. So, but down in IL, the estimators constructed from observations that are not in IL, and then you get data back just by solving the moment equation that you got from the name without the moment equation, which looks like this. Solve that name without the moment equation with the alpha half plugged in and the gamma half plugged in, and then you simply get standard errors. Okay, so this is our algorithm. Right, you gotta get you started with a gamma hat, you have your orthogonal moment function, you get the alpha hat from this exactly function here. Okay, and then just minimize that to get your alpha. And then there's the rest of the alpha. All right, how does it work? Okay, so let me talk about that. Let's look at that example. The theory, there's some statistical guarantees there. I'm going to skip that. Monte Carlo. The second paper compares performance of this for the neural net alpha. Okay, with what we labeled, and they didn't make us change the label and say that they are neural net estimation of the average treatment effect, which used an inverse propensity score neural net estimate. So the Monte Carlo design is the same. We use the same design that they used, and so there's no ID at all. Here's where it was taken from, and here's how the data was generated, exactly how they did it. Okay, 747 observations, an outcome Y by treatment T, and 25 continuous binary confounded effect. So it should be T, but anyways, we do it over there. Okay. So we use exactly the same algorithm that they did, except we didn't use the inverse propensity score rating, we used this automatic method instead. Okay, and we find a large improvement. Okay, so how large? This is the benchmark. Okay, so this is the dragon net estimator. 0.146 was MAE, right? And we get 0.110. Okay, so a large fall in the accuracy, a large increase in the accuracy of the estimator when you use this automatic method, and you can't read it, apologize for that, but it's 95% coverage. Okay, for the coverage probability. There's also a reinforced version of that, I think you might as well, but it's still being dragged. Okay, and what's going on, we think here, we speculate, is that, doing a neural net estimator of a propensity score and then including it, put it inside the estimating equation, that's probably a bad idea. Right, because the propensity score gets close to 0 or 1, it makes that inversion pretty unstable numerically, and so we think that that's probably the idea. We're not doing that. We're not doing any inversion of anything anywhere. Go back. What we're doing is we're minimizing this objective function for neural net. Right there, right. This objective function for this neural net here. We're minimizing that. No inversion. Okay, we're just doing a neural net estimation to estimate out. And what we're doing is, we're using, just using the characterization of alpha as the minimum of this objective function. So there's no inverted anything for this. Okay, and so I think maybe that's the source of improvement of anything you have large improvement. It works, large improvement over the existing technology and doing device machine learning of speaking of fact using neural net, and so that's promising. Okay. So I think I'm going to stop here. My time's up, and so there's automatic method. What it does, it allows you to get a much improved estimator using neural nets here, and also allows you then to, anytime you're doing a regression of pretty much any kind, gives you an automatic way of estimating the bias function to estimate the parameter in different ways. The bias with the first and machine learn on this, so I did it more. I think I'll stop.
Any questions on the
that is about the rotation, the implementation. So you have, if you go back a few slides where you define the estimator of alpha 0 or alpha hat. Right. Yeah, this one. Right? So here you have both alpha of xi and alpha in this notation. So what is alpha of xi?
Literally, the function, whatever it is.
I see. So you I see that just written down. It's the other part is also alpha. Is there an alpha?
But no, because it's a functional alpha, right? I'm sorry, I don't even know that it's a functional alpha.
Right, but the alpha inside is M is also a function of X, no?
It is, but this object is a functional of it. It does not involve point evaluation. No, it's just going to go to it's a great question, actually. Great question. Let me go, there's the average treatment effect. See, so what you're doing is you're plugging into the M. So whatever the M does to alpha to get you the object you're interested in, that comes out inside of the investment.
So there's another thing I was when you define the when you write gamma in terms of alpha, when you write some previous slide with that, no. Right. So here, sorry, the second line, the expectation of NW gamma is equal to the expectation of alpha 0x gamma x.
Yeah.
So that's essentially the ridge representation, right?
That's right.
And I guess that's why you need some linearity in terms of.
Yes. So the way you deal with the nonlinear case with multiple gammas is you take the co-derivative with respect to whatever gamma you have to do it one gamma at a time. Okay, so what would happen is your orthogonal moment function would have one of these for every gamma. This specific alpha. You have one of those for every gamma, you take co-derivative it's the lead representative that you can estimate it automatically just the same way. You just put in, I'll show you, let's see, here, instead of M, in this objective function, you put the hit over it. So it's a little more complicated.
It's fun to do that.
It's possible.
Not a limitation of that.
No, it's no limitation, that's a very big, you know, the derivatives generally, for all, lots and lots of examples, it's easy to compute that, so you're just taking the derivative of, you know. Respect to the P, yeah, you know, a little bit in the gamma, it's easy to compute, and then you just plug in the derivative. It's a little bit harder because, to get it to work theoretically, we have to do more cross station. So the third cross step you have to do, because in general, the code, you know, it won't just depend on alpha, it'll depend on again. Right, and so we pull that and something, you know, put together the theory of work.
May I ask one more question? Obviously, you kind of started off, maybe, you know, illuminating Hansen, Richter, and all the way to automatic parts. And that works for, you know, all our machine learning methodology, and you also talk about more general estimation problem here. What is the next step?
It's a good question. What is the next step? I'm sure there will be one, but I don't know. So, yeah, great question.
Oh, we, you know, have a people operate this country. So that's the better of the message.
Yeah, sure.
This, they are in parts of the fact. Okay, so my, the kind of part. Okay, so my second question is, something that, kind of imagine, you know, many, treatment.
Okay, so let me be direct about this. So, and completely above board, which is directly applying this for neural nets doesn't work. Because if you go look at the, what it can show up for the alpha here, the M is the derivative of the neural net with respect to the margin, you know, the walk, the D. And actually, we don't have engineering to do this, but nobody does. Nobody knows how to control the behavior of the derivatives of neural nets. Right? It's all of the derivatives are about, you know, these for error. Very great, and that's what it's. I just didn't want to put it in here. For a certain kind of derivative, you can do this. If you're integrating over some fixed plate, look at the integral over some fixed plate of the derivative. You can do integration by parts first, and then it gets rid of the derivative of the estimate, and then you can do this. And that's been the paper with the whole Victor, the earlier one, so paper. But yeah, it's hard to do actually. Hard to actually get. This is the word. We don't know how to do it actually for the average derivative for neural nets. Okay. The weighted average derivative for fixed plate guy, I know how to do it.
I actually, I remember that I heard when I hear your comments. So, this definition corresponds to what we set up the zero order condition, set it to zero for two functions, so that it's means zero. And then if we go beyond that, then we have first order, so that your estimate is insensitive to choices of the outcome. And if we go to second order.
Good question. Second order. You want to do a second order bias? What's the next? I think some work on trying to do that, second order bias. We haven't quite in the case of Not the machine learning base, there's this whole there's on priority ones. Which, some players are being brought up, think about, kind of what some priority that.
So the one year book on the impression for the experience for using IR. What do you think for
Not really necessarily in the application, very high for it means that you go back to the course of the draft. What do you think is necessary? Probably not. I don't think so. At least for marketing.
it's good enough?
Yeah, it's, of course, you're kind of benefiting from the fact that, it's a little smaller and more, a little thicker and covered there, and it's kind of guess. Yeah, but for two kind of content, we haven't worried about it. And again, you can't actually show these things, it's like you sort of similar picture for the mind trial. You can't, I apologize, you can't see it very well, but you don't just kind of pick up and fail on it, right? So then cancel out or up or fail and you get it kind of like. Oh, I'm sorry, this is. Oh, you can't see it, but but you do have a bit of a pick up or fail and more fail and you can't figure it out. So there's some bias if you're really one-sided. You're doing one-sided test about your grammar index that you might want to think about for the bias strategy, but it seems to be pretty common to for the two-sided problem. So very well. It's important.
So they realize decided to use values as the image. So somehow solutions that some people, that even if you use the values afterwards, you're going to have to on the back of the not good, so another.
That's a great question. I think an application, if it comes down to a problem with the overhead, right? It's just the density is 4 and then 0 and it's a bit 1, right? One of the applications that you estimate it gets close to the value. We don't know, or one was hopes that maybe this helps take care of that in some way, but we don't know that. That's a hard problem. Yeah, what people do in practice, right? Because they turn their data and even though it's a different end student of that, it's actually about the usual on those something done. That's what people do around the page. And once you do that, at least the automatic method provides a way of bias correcting that, right? In a way that not involving inverting the density score, and that's the